for your kind introduction. And thanks a lot for inviting me to coming to Brazil. So it was my first time to travel to Brazil. So it's a good experience. I hope we can repeat that. So maybe TU Darmstadt or Darmstadt is not the most famous place in Germany. So if you take a look at the map of Germany, you're located here, where this arrow is, and the letter A is just placed over Frankfurt. So if you want to know where we are, we're just 30 minutes away from the airport of Frankfurt. I think everybody traveling to Germany or to Europe knows where the airport of Frankfurt is. So we are quite at the heart of, let's say in the terms of transportation, in the heart of Germany. So if you go to our city, that's a small city, we have about 120,000 inhabitants. So the university has places right at the center. And we also have a huge campus a little bit outside. So here's a huge forest. You can do jogging and have a lot of relaxing after your work. And I think that's a unique feature for German university because we have our own airfield here in Israel. So we do have experimental airplanes and we're also working in the field of aerodynamics. That brings me to the next point. So, my institute is now part of the cluster that's called Center of Smart Interfaces. The idea was to design engineering surfaces specifically to certain purposes. So the initial idea came from aerodynamics. So they were looking for smart coatings, for smart structures for wings to reduce aerodynamic drag. This is how it started. They were then talking to other guys working on combustion engines. The thing grew bigger. Then they thought, okay, it would be cool to have chemists, it would be cool to have physicists in this center working, let's say, on phenomena that are related to the interaction of fluids, that can be a gas, that can be a liquid, with a surface. And this is how the entire thing was established. So we have now 5 professorships that are really in the center of smart interfaces, and we have about 10 professorships that are associated with the center. Our objective is to have an interaction between the natural sciences and engineering sciences in order to enhance the properties of surfaces. So there are several research fields that's called static and dynamic wettability. Well, that's essentially, that's wetting. You also can imagine that's microfluidics. This is also the interaction of biological objects. Next thing is near-wall reactive flows. Well, just if you think in a combustion engine, you have combustion near the wall. So this is what they're interested in, is how to enhance combustion processes. But there's also a connection, for example, to heat transfer. So this is effective heating, heat exchange. Here comes the aerodynamic guys. Initially they were the big center of this cluster doing aerodynamics, and now there are only 2 left. So things changed a little bit. And there's a close connection also to multi-phase flows. So once you have a liquid, you have a gas flowing over a surface or through a porous medium. There can be very interesting phenomena. So we also do have mathematicians working on these problems. Right now we are not yet fully established. We are building a new complex where this entire center is put together. And I think that's also a quite unique thing. So we have in one building professors for mathematics, chemistry, physics, material science, in the material science department, and mechanical engineering. And the idea is to put us together and to work together. And this will be inaugurated next year in May. So right now we are more working in intermediate premises. And just I would like also to advertise in the Department of Material Science. We do offer a master degree in material science which is taught completely in English. So we will also be happy to have students from all over the world. The only requirement is that you have to have a bachelor's degree in chemistry, physics, mechanical engineering, of course also material science, but we are quite open. So we now have mechanical engineers, we have physicists, we have chemists in the courses. And also here the idea is to have a certain diversity in background to create stronger links between the disciplines. Okay, now let me go to the science part of the talk. Today I will talk about two topics that are slightly interrelated. So the big topic is, I want to introduce to you microsystems, or the development of microsystems for atherosclerosis research, so for biomedical application. And you will also see that for this purpose you need thin polymer films. And then polymer films are interesting from a physical point of view of themselves, so this is also an interesting field of research. So we'll talk about that later. Now, first, talking about atherosclerosis. So that's one of the major problems in health we have right now. So this very often affects your arteria carotis, so that's the blood vessel that comes from the heart. Here on this side you have a bow here, and a part of the blood is going to the brain and another part to the lung. And that's exactly in this bow where, let's say, cholesterol and all this stuff is accumulating. So initially the blood vessel is very healthy, you have a normal histological tissue. But over time, so if your lifestyle is not healthy, you accumulate essentially first-time lipids. So when you're in the 30s and you consume too unhealthy lipids, the vessel will start to become more and more narrow. So you're developing a stenosis. And typically, so starting from your 40s to 50s, this becomes dangerous. So you have also, now not only the lipids, you also have a mixture of extracellular matrix proteins that are here in this area. And the dangerous thing starts from this entire thing that is still sealed under the epithelium. Once that breaks open and the extracellular matrix proteins are exposed to the blood, because then the entire cascade of blood coagulation can start. And this is how thrombus forms, and this is what gives you another starter for myocardial infection. It's a heart attack or stroke, because this agglomerated blood then seals your vessels in the brain or in the heart. So that's the background of it. If you take a closer look and look at a blood vessel from a physicist's point of view, what do you have? If you have a vessel, essentially you can see it as a sealed tube. And you have the lumen, you have the epithelial cells, you have some muscle cells in here, giving the elasticity. The elasticity goes away over the time. And you also have calcification. You have some biological or chemical functionality, so you have signaling and O-signaling, which essentially suppresses platelet adhesion. You have collagen in the connective tissue. And this illustration shows something that always happens in your body. So when our blood vessels, they're still flexible, they're very robust, but still, once in a while they break open, you have small lesions in these blood vessels, and small amounts of blood are bleeding into the tissue. So this is illustrated here. And then we have a natural mechanism, a natural repair mechanism that instantaneously repairs again this damage. So, and let's say the intelligent glue to seal these lesions, these are blood platelets. You know, these are the small discrete particles we have in the blood, and they're responsible for sealing essentially such lesions. Now, if you take a closer look at how all this wound sealing occurs, That's a rather complex process. It's a complex process that includes, let's say, biology, chemistry, so you have a lot of signaling, but also physics. So you will see that the flow conditions play a major role in it's called mechanical transduction. So it's also a signal that comes from outside to the platelet and triggers the platelet to do something. So what usually happens is once here you have a small lesion, this collagen, which is the connective tissue, is exposed to the blood. So we have some platelets adhering to the collagen, and these platelets are telling their fellows, hey, come on, there's something wrong, you should do something. So that's this inside-out signaling, so they release so-called platelet factors, just attracting other platelets. This is what happens here. And this then leads to an aggregation of a platelet plaque that, in the first instance, seals the lesion. So to show it a little bit more in detail, so you have the blood flowing through your vessel. You have all these corpuscular components in your blood. You have red blood cells, you have lymphocytes, and you also have platelets or blood platelets or thrombocytes. These thrombocytes are these small discoidal particles. Then the blood flow, and then remember you have this parabolic stream profile in a blood vessel. So there are also platelets that are at the boundary of the blood vessel. They're rolling across the blood vessel, and still they maintain the discoidal shape. But the point where they notice that there's something wrong, so their receptors detect something that shouldn't be here, which can be an extracellular matrix protein, that also can be signal. They change their shape, so they get a globular shape, and they develop philopodia. And in these philopodia, you have the focal adhesion points, where you have the receptors, and the platelet is able to attach to the surface. Imagine the platelet has one problem. It's a corpuscular particle rolling in your blood. You have a, let's say, pulsating flow, because you have your heartbeat, but this platelet has to stop at the right place. And this is done by anchoring with these integrin receptors on the right spot. And this is how these philopodia develop. So it's still rolling a little bit. The philopodia are attaching to the surface. It's rolling further. And then at a certain point, the platelet manages to attach to the surface. And the shape change continues. So then it looks like an egg in a pan. And finally, it flows over the entire surface and seals the surface. So this is what is called the hemisphere-shaped platelet. That's a rolling ball shape. And this is the full irreversible spreading on the surface. So what you see down here, this is a wide variety of integrin receptors that are necessary or that mediate binding to the surface. So for inside-out signaling, there are some glycoprotein receptors that are responsible for the interaction with the surface. So one is this GP1B, which binds to von Willebrand factor. So this is the factor we will talk a little bit more today. So once this started, there's also the activation of other integrin